However, if you consider the special case where xi's are independent, x1 x2 xn are independent, then these formula all these formulae will simplify, right. So, in particular for example, for the maximum what would you get? You have the joint CDF evaluated at z z z, but the joint CDF will factorize product out, correct. So, this will become fx of z power n, right. So, here again you will have the complementary CDF to the nth power, right. In particular, if x1 x2 dot 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 xn are independent. So, first of all first let me do the case when they are independent. Okay. So, I will have f z n of z will be equal to product f x I of z, z is equal to I is equal to 1 through n, is that correct? Because my joint CDF will factorize, right. Further, if x1 to xn are independent and identically distributed, IID means this is the first time we are encountering this, I think, independent and identically distributed. It is just as the word says, right, if they are independent and they have the same CDFs, which means all these fxi's of z are the same function fx, right, with CDF fx, then the maximum will be distributed as, this will be simply the, so all these are the same function now. So, now it will be the nth power, right. So, if they are independent you will multiply the CDFs, if they are independent and identically distributed you will take nth power of the common CDF, well I should say z here, right. Fine. Similarly, you can do the same thing for the minimum. So, in this case what would you get? You will get f. So, the complementary CDF of y as the product of the complementary CDF of each of these x's, and in the case when they are identically distributed you will have the nth power of the complementary CDF, right. Next, we have for the minimum we have f y n of y is bar is equal to product. So, I am still with the independent case, okay. Product I equals 1 through n, it will be f x bar of well f x I bar of y, correct. So, because of this formula I had here, and this f bar will product out, the complementary CDF will also product out, right. When x1 to xn are independent and f y n bar of y is equal to f x bar of y to the nth when x 1 to x n are independent and identically distributed IID. Okay. Okay, so far. Okay, so let us consider one or two examples. So, that completes the theory bit. So far okay, any questions on this?
So, in the 3 stages 1, 2 and 3 self-random variables having function, why not we need to prove that there is random variable with respect to 2?
So yes, that is what we need to prove, but here there was an easier way out. You directly proved that pre-images of semi infinite intervals are events. You exploited the fact that these x 1 x n x 1 through x n are random variables.
It is also possible there is random variable with respect to 2. And
Yes, it is. So no, it is a random variable with respect to, I mean there is random variable just means the measurable function, finally it should be a measurable function on omega, right. You can prove it whichever way you want, whether you want to prove that f is Borel from R to R, that is fine, or if you want to prove that pre-images of all Borel sets are f measurable, that is also fine. Here we proved that pre-images of semi infinite events semi infinite intervals are f measurable, that is enough. See, usually the definitions of measurable function we make in terms of pre-images of Borel sets, but it is very difficult to verify that, right, because Borel sets can be so complicated and their pre-images can also be quite complicated, and you have to do this for all Borel sets. So, what you do is just verify for the generating class, and it then follows that it holds for all Borel sets, right, it is something you need to prove. Okay. Examples. Let x 1 and x 2 be independent identically distributed, let us say uniformly distributed random variables. So, you remember uniformly distributed random variables, right. In 0 1, let us say. Let z is equal to max x 1 x 2 and y is equal to min x 1 x 2. So, you have x 1 and x 2 inducing a uniform measure on 0 1, okay, and they are independent. Okay. So, they are independent and identically distributed random variables, and you are looking at the maximum of the 2 and minimum of the 2. Okay. The question is how are they distributed. Okay. So, are there any guesses on how qualitatively they may look? So, you are taking 2 identically distributed random variables on 0 1 independent, and you are taking the larger of the 2 and the smaller of the 2. Sorry, okay, qualitatively. See, it is clear that both z and y have to take only values in 0 1, right. We are talking about 2 values, 2 random variables which are both taking values in 0 1, right. We know that z and y have to be dependent because z is bigger than y, right, fine. And if you look at the distribution of z, what do you think it will look like? It will be, so it will be more towards 0 or more towards 1, yeah. So, z will have more mass towards 1 and y will have more mass towards 0, that is what you would expect, right. So, let us actually verify this with our formula that we just derived here. So, we have f, so what is f x? So, f x 1 and f x 2 are both, so f x 1 of x will be x, isn't it. So, will be 0, x and 1 depending on whether x is less than 0 or x is in 0 1 or x is greater than 1, right. This is our CDF. So, from our formula there you can immediately see that f z of x, f z of z if you like, f z of little z will be equal to f x of little z to the square, right, f x, well by f x I mean either f x 1 or f x 2, they are both the same, right, is that okay. So, this will be equal to 0 z square or 1 depending on whether z is less than 0, z is in 0 1 or z is bigger than 1, correct. So, that looks like, so if I plot capital F z of z, it will look like a parabola, right, fine. And you can see clearly that this function is differentiable except at these 2 points, right, and you can actually get a density as well, right. After all, x 1 and x 2 are continuous random variables and z also turns out to be a continuous random variable. So, your density PDF f z of little z will be what? Be 2 z, isn't it, 2 z if z is in 0 1 0 otherwise, right. So, your little f z will be like this, little f z will be 0 outside this, and here and here. So, at 0 and 1 there is no derivative, but you can define it as whatever you want, does not matter, and in between it is equal to 2 z, right. So, it will look like that, right, is equal to 2, right. So, the PDF looks like okay, and that is a valid PDF obviously. So, you see that, so more of the mass is towards 1, right, it is likely to be closer to 1, the maximum is likely to be closer to 1, and similarly you can prove that f y is the minimum, right. So, f y of little y will be equal to, so f y bar of little y will be equal to 1 minus y square, isn't it, will be 0, sorry, will be 1 minus y whole squared or 0 depending on whether y is less than 0, y is in 0 1 or y greater than 1. Okay. And from here you can get the density again. Okay. Is this correct or am I missing something? So, I am just taking the complementary CDF of x, which is which is 1 minus y, and I am squaring that. I think this is correct, right. So, the PDF will be, now if you plot the PDF, it will be the derivative of this, that will look like that, right, be twice 1 minus y, right, it will look like that. So, the minimum has more mass towards 0, as you would expect. Is that clear? Okay. Any questions? Yes.
How to find the PDF from complementary CDF?
So, this is complementary CDF. So, 1 minus that will be your CDF, right, and you differentiate that, you will get a PDF. Okay. Okay, let me just do one more example in the 5 minutes that remain. So, example number 2, let x1 x2 dot 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 xn be independent random variables which are exponentially distributed with parameters. So, exponential is a parameter is by one positive parameter lambda, right. So, I am going to give you the parameters lambda 1, lambda 2 dot 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 lambda n greater than 0. So, I am telling you that these are exponential random variables, they are independent, but they are not identically distributed, they have different parameters. Okay. So, in this case what? So, so if you have f x I of x will be equal to 1 minus e power minus lambda I x for x greater than or equal to 0, correct. Remember this, remember CD exponentials, right. So, this is the CDF, right. And for x less than 0, this is 0, okay. It looks like that. Okay, now, if you look at y is equal to minimum of x1 dot 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 xn, I am looking at the minimum of these independent exponentials. Okay. So, now what happens? So, I will have f y of y will be equal to product, well I should say f y bar, is not it, f y bar is equal to product I equals 1 through n f x I bar of y, correct, because now x i's are independent, they are not identically distributed. So, I cannot take nth power, correct. So, this will be equal to what? So, f x I bar will be e power minus lambda I x. So, I am multiplying. So, I am multiplying product I equals 1 through n e power minus lambda I y, correct. Yes or no? And this will be equal to what? E power minus sum over I equals 1 through n lambda I times y. What does this mean?
Parameter changed to lambda plus 1.
It means that y is also an exponential, right? Y is an exponential with parameter sum of the lambda i's. So, if you take, so what does it mean? So, if you take n independent exponentials with parameter lambda 1, lambda 2, lambda n, then the minimum is distributed as also an exponential with parameter sum of the lambdas, right. So, y is, I can write exponential with parameter sum over I lambda I. Okay. You can also compute the distribution of the maximum. What would you do? You will just multiply, not the complementary CDF, the CDFs themselves. You will multiply all these guys, but that you will not get anything nice. You will get some distribution. You will get the product of all these guys, right. So, the maximum will be some distribution. The minimum is an exponential. So, the minimum of independent exponentials is always an exponential, and the parameter is the sum of the parameters of the individual ones. So, this has a very nice practical interpretations. Remember that I mentioned exponential is this memoryless distributions that that arises frequently in let us say radioactive decay, right. So, let us say that each of these corresponds to the ith sample, maybe they are all different radioactive elements or something. So, they emit alpha particles at different rates, right. So, and each sample, ith sample, let us say has inter emission duration is exponential with parameter lambda I, and you let us say that they all are emitting at one point in some place, and the minimum of these is the time to the first emission, correct. You have all these independent samples emitting. So, if they are all independent exponential times, the time duration for your first, the time for you to see the first emission coming out is also an exponential, right. Is that understood? So, yeah, so this has lots of nice properties, right. So, this is these inter emission times being independent exponentials is a very well known process called the Poisson process. Okay. So, it has lots of nice properties. We will not study it in this course in any great detail, but there is another course called stochastic modeling, right, which will be offered next semester. That is half the course is about these Poisson processes. Okay. So, that is just FYI. Okay, but all you need to know now is that the minimum of exponential is also an exponential, independent exponential is also an exponential. Okay, I will stop here.